A very good morning to all the students. I am Dr. Hima Bindu from the Department of Mechanical Engineering from the Institute of Aeronautical Engineering, and I'll be dealing the subject robotics, and my today's topic is generalized equation of motion in robotics. Right? What do we mean by the term generalized equation of motion? What are we defining here, and what are the terms and conditions being applied in this particular generalized equation? All that we will be studying in today's session. Right? So in robotics, the generalized equation of motion is nothing but particularly for when we consider a robot manipulator, we can derive the principle of Lagrangian mechanics, right? When we come across the generalized equation of motion in robotics, it is particularly used to define the principle of Lagrangian mechanics for the robot's manipulator, right? So this particular equation is used to govern the dynamics of the robot, considering the relation between the force on the system and its motion. Right, based upon the force and the motion, we will be defining the governing equation in terms of dynamics of the robots, which shows the relation between the force and the motion. So in that, the first step is to define the system configuration. When we need to write a generalized equation for the robot, we need to first define the system configuration. So what is the system configuration? It depends upon the degree of freedom. Yes or no? When we take any robot manipulator, at how many degrees of freedom that particular joint is rotating or revolving, we need to have an idea. Right? So considering the robot's manipulator with respect to the degree of freedom, we need to define the system configuration first. Right? So let us consider Q is equal to Q1, Q2, or so on up to Qn with respect to the transverse whole to the power of t, right? Where these are the joint angles and positions, etc. Right? Where these are the joint angles and the positions. Now here, the time derivation for this particular generalized velocity can be written as Q dot is equal to Q1 dot, Q2 dot, and so on up to Qn dot whole power t. Right? So the time derivation with respect to the q at the generalized velocity can be written as q dot is equal to qn dot, q2 dot, or so on up to qn dot whole power t. So first, to write a generalized equation, we need to define the system configuration with respect to the degrees of freedom, where q will be taken as q1, q2, so on up to qn whole power t, and with respect to the generalized velocity, we will be writing as q dot, qn dot, q2 dot, or so on up to qn dot whole power t. Now, next we need to define the kinetic energy T. Right? Next we need to define the kinetic energy T. The kinetic energy T is nothing but the sum of kinetic energies of all the links. If we have 1 to 5 links. So link 1 plus link 2 plus link 3 plus link 4 plus link 5. That is the kinetic energy T1 plus T2 plus T3 plus T4 plus T5. That is the sum of all the 5 links altogether will give you the kinetic energy. That is T of Q and Q dot is equal to 1 by 2 Q dot T into M into Q and Q dot. Right? The kinetic energy T is being written as half Q dot T into M into Q dot. Right? Where M is nothing but mass inertia matrix, which is a positive definition matrix depending upon the configuration of the Q. Whereas the potential energy, we are taking it as V. Right? The potential energy, we are taking it as V, which gives us the association between the gravity or the elastic elements in the system, where the potential energy works as a function of Q, right? The potential energy will be working as a function of Q, and the Lagrangian function is nothing but, we determine it as L, where L is equal to Q into Q dot is equal to T into Q dot minus V of Q, minus the V of Q. That is how we write the Lagrangian function L. L into Q comma Q dot is equal to T of Q comma Q dot minus V of Q. Now we need to just define the generalized force, that is nothing but Q, right? We need to define the generalized force, that is nothing but Q. So this particular generalized force Q is acting on the system, which is related to the external force and torque applied to the robot. Now we will be writing the Euler's Lagrangian equation, right? Now we will be writing this particular Euler's Lagrangian equation, which is written as d by dt of dou L by dou Q dot minus dou L by dou Q is equal to Qi, where I can be considered as, I can be taken as 1, 2 or so on up to n, right? Where I can be considered as 1, 2 or so on up to n number of components. Now substituting this Lagrangian in this particular equation, we will be getting mq of q dot plus c of q dot into q dot plus g of q is equal to q. We will be substituting the Lagrangian equation in this particular equation, where mq is inertial matrix, C is nothing but the centrifugal force matrix, and G is nothing but the gravitational force vector, right? Where M is inertial matrix, C is the centrifugal force matrix, and G is the gravitational force vector, whereas Q is the generalized force, right? So this is how we will be writing generalized equation of motion, right? So based on this particular equation, we will be writing the generalized equation of motion in robotics. Next, what do we mean by external forces? What are the various external forces which come across in robotics? That is also one of the important aspects, right? The external forces are nothing but which are critical concepts in robotics, which are used to interact with the environment and the performance tasks. So here we have few external forces which we have in robotics, that is environmental interaction or disturbances or force sensing, right? These are few of the external forces in the robotics. What do we mean by environmental interaction? That is when the robot has to interact with the environment. It should have some external forces arised, right? Including the contact with the objects, or whether it is a ground reaction forces, or whether it is with the human interaction. These forces must be able to sense and avoid the gripping or walking or achieving the specific task, right? It should come across these particular sort of external forces in the robotics, right? When we come across disturbances, what do we mean by disturbances? That is when we have uneven surfaces, or when we come across the wind or unexpected forces, right? It should withstand itself. The robot should withstand itself, or collision, when we come across any collision with the other objects or other obstacles, right? There should be an advanced control is required, right? An advanced control is required to detect these particular disturbances. In order to detect these unaware disturbances like uneven surface or wind or collisions with the object or collisions in the environment, right? These particular disturbances the robot should be able to detect, right? When we force sensing means like force sensing such as strain gauge or tactical sensors, or depending upon the behavior or safety, or depending upon the external forces, or depending upon the delicate or the complex. So the robot should be able to sense the forces from either of the obediences like behavior or ensuring the safety, or depending upon the complex tasks being coming across the robot, or depending upon the effective operations, right? Any robot should be able to sense the external forces such as environmental interactions or disturbances coming across from the environment, unexpected environmental condition, or with the help of the force sensors, right? Next is the soft contact model in robot. What do we mean by soft contact model in robot? Soft contact is already we have seen the soft robotics, right? What do we mean by soft robotics? That is the end effector, whatever we are designing, or the end effector, whatever we are constructing. That material which we are using is very soft, right? That is generally we are using that sort of soft robotics in healthcare centers or in education institutes, where the touch of that particular end effector will be soft, where the material which we are using is very soft. So here again, a soft contact model in robot refers to the mathematical and computational framework being used. Right? When we have a mathematical and computational framework coming across, the interaction between the robot and the surface or the object, when we are contacting with non-rigid, but there will be some degree of compliance or flexibility or the deformation, right? That is, a soft contact model in robot refers to the mathematical and computational framework where it is used to involve some of the degree of compliances or flexibility or the deformation. Or this particular soft contact models are generally especially used in scenarios where robots interact with soft or delicate objects. Just now, as I've told you, generally these are the soft robotics are generally used for coming in contact with the soft or the delicate objects. So there we use this particular soft contact model in the model in the robot. That is, when we have the robot components that deform upon contact. So that is known as the soft contact model. That is, a soft contact model in robotics is a scenario where the robot will interact or handle the soft material, soft objects. Right? Next is the key aspects of soft contact models. What are the important key aspects that we need to consider? Right, that is compliances or deformation, or it may be on the contact force models. Right, so when we come across the compliances and deformation, generally these are more reliable or these are more adaptable for the applied forces, right? That is, for the soft contact model is used for the elasticity or flexibility, right? The soft contact model are generally used for elasticity or flexibility of the material, which are used as the where we use a deform and the absorbed energy, or when we come across the spring, or when we come across the soft materials, then the deformation is being coming into account, right? Next is the contact force model. What do we mean by contact force model? This is again including the force displacement relationships. Right? The contact force model is again including the force displacement relationships, where here the elastic deformation or more complex models for non-linear or viscoelastic material is being used. Right? For the contact force model, we will have the relation between the force and the displacement that describe the contact force developed in the robot interaction, or which also depends upon the complex model for the non-linear or viscoelastic material. So these are the key aspects which we come across in the soft contact models in the robot, that is compliance and deformation or the contact force models. Right, and the third one is the friction model or energy dissipation or surface properties. Right, these are also some of the key aspects. What do we mean by friction model? Friction model means it plays a very important significant role in soft contact interaction. That is, the models such as the friction or advanced formulations like dynamic friction model can be incorporated to simulate the tangential force during this particular sort of the contact. right? That is known as the friction model. Or energy dissipation means which involves energy dissipation due to material damping or effects. Highest, or we have any, when we have any sort of effects, or when we have any sort of material damping, then this particular energy dissipation is being involved in the soft contacts, right? Or when we have, when we need to when there is an energy absorption, or when there is release during the interaction, the energy dissipation comes into account. Or when we come across the micro scale properties, or when we come across considering the accurate simulate soft in a contact interaction. The surface properties also come into contact, like delicate objects, manipulating the delicate objects, or scenarios like gripping. The surface properties come into the account. Right. So we have few examples, like what are the programming, or what are the models which we can consider for the soft contact models. That is Hertz contact model, DMT and JKR models, or the spring damper models, right? We have three types of models, that is the contact model, DMT and JKR model, or the simple damper type of the model. So these are the three examples of the models which we, and we also have two other theories like beam theory, right? So these are few of the contact models which we can consider as the examples, right? Where this is Hertz contact model. Means what? What is happening here? We need to describe the contact between two elastic bodies, or with respect to the curved surfaces, right? That is known as the Hertz contact model. Or when we come across DMT and JKR models, here we are incorporating the adhesive forces used in the different scenarios, like adhesive play and role in contact dynamics. So that is known as the DMT and JKR model. Or when we are capturing both the immediate elastic responses and the time dependence viscous effect, then we come across spring damper type of the model. That is, this combination is between the elastic element and the viscous element, right? This is between elastic element plus viscous element. When we come across these particular combinations, then that is where we come across spring damper model, right? Next is the beam theory. Beam theory means what? It is a theory which is used for modeling contact where bending and shear deformation are significant, right? That is generally near the robot finger or near the gripper. This generally occurs near the robot's finger, that is near the end effectors, or near the gripper. This particular type of beam theory should be very importantly used, where we come across the bending and shear deformation, right? Next, simulation and implementation. What are the various simulations and implementations which we come across? That is ROZ or gazebo. This is the new simulation which have come into account. That is ROS, gazebo, or the custom simulations which we are mostly using, right? The soft contact models are capable of implementing in various robotic simulation environments, that is ROS, gazebo, or customer simulation. And these particular models depend upon the specific applications and material properties for the simulation, right? And these are the references which we have come across. So in the generalized equation of motion in robotics, we have discussed about how to write a generalized equation of motion in robotics with respect to the Lagrangian equation, right? And we have seen the various simulation and implementation. We have come across the soft contact models. We have four type of soft contact models, that is Hertz contact model, DMT, JKR model, and spring damper model, and the beam theory, right? These are a few of the examples for the soft contact model, and we have come across the various key aspects for the soft contact models, that is compliance and deformation, contact forces, and the friction models, energy dissipation, and surface properties. And we have already discussed, we have also given a brief introduction about soft contact model in robotics and external forces which are being used in the robotics, right? So this is all for today. Signing off for today, Dr. G. Hima Bindu. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.